Okay, this is the L'Hopital rules for the indeterminate form of 0 over 0. Okay, what it says? It says that if we have two functions f and g, both continuous on a and b, and both are differentiables in the open interval over a to b, then suppose that exists a c in this closed interval, which is a compact set in the real numbers, that make both functions 0, which will be the indeterminate form. Suppose also that, of course, the derivative of gx is not 0 for all the x in u. But what is u? U is the set that is the intersection of all the numbers in the open set AB and some dilated neighborhood of C. What is a dilated neighborhood of C? Basically is all the numbers that are in around C. Let's say C is here. All these numbers except the number that we are asking for. In this case, C will be this whole. We are not including that number in this set. We are included all the numbers around. So if we have the interval, let's say this interval is coming from here to here, the intersection will be only this, right? Except the number C. That is the neighborhood intersection that I am talking about here. So for that, we have the limit of x that is tending to be c of the derivative of each function will be a number that exists, which is not indeterminate. It's a number that exists in the real numbers. Then the limit of the original function, the quotient that we wanted to have, will be also the same number. To prove this, we need to remember a few things. This looks like obvious, but let's recall what is said. It's basically for every function in a domain, within the domain D and the real numbers, let's C be an accumulation point. An accumulation point is, all the numbers in the real numbers are accumulation points, but sometimes we are not working with the set of the real numbers, we are working with another type of sets. So we need to call it out that we need that these numbers, these elements are accumulation points. And basically that they will have numbers very, very, very close, and wherever you take it, you will find another number very close inside. Even if you have this neighborhood super small, you will have inside numbers or elements that are super close to it, and always will approach to this number. This basically is the meaning of accumulation point. I will actually record a video for that later, but for now, just take it as a number in the real line. Yeah. Converges. We have a point. Then the limit of the numbers that are tending to be C for this function will be equal to L, that L is, as I said, a number in the real line, if and only if for every single sequence that we have converging to C, converging to this number C in D, of course, with the exception that the sequence is not exactly the same as C, it are just converging to C. For all n, the sequence of the function evaluated to this sequence also converges to L, right? So if we have a sequence that is convergent to C, the evaluation of the function of that sequence will also converge to the limit of this function to L. Okay? Now let's go to the proof. So we left a sequence x of n in U that converges to C, right? Using the Cauchy mean value theorem of f and g on the interval, let's say from xn to c or c to xn. Remember the Cauchy theorem, I recorded a video for that, it's this one. It just said that if we have two functions f of g that are continuous and differentiables in a specific interval, that exists a point c in the interval such that this equation is satisfied, right? The derivative here, and all this subtraction is basically a static number, right? So we can write that here as I have it here, but instead of put the number c, I am including the sequence that will converge to c, okay, here, and the sequence of x that will converge also to c, right? If we divide both sides by the derivative of g evaluated to the sequence cn, we will have I will show you in a moment what we are going to have. We are going to have this form, right? We will divide this, and basically all this part will be equal to the derivative of the function. Okay, let's come back to this place. So by assumption, we said that the derivative is different to 0, right? For all the x in u, and of course the g, whenever it arrives to c, it will be 0, but we must have all the other numbers around different to 0, and that is by the Rolle's theorem. You remember the Rolle's theorem, basically, that we will have the derivative to 0 if they change, but if we said that they will not change, it's because it is either strictly increasing or strictly decreasing, so we will not have the other numbers equal to 0 in the derivative. Okay? Then so in this case we have, as I show, this function which is coming from the Cauchy mean value theorem. Then for the second xn that is converging to c, and c is also between these two, it follows that the sequence cn is tending to c also, and this is because what I recall it here, number 1, because if we have a sequence that is going to a point c, we also have the function to go into the evaluation of that as a limit. Therefore, if this limit exists, then this also limit will exist. This is the x that will tend to n to c, right? This is the sequence, and because these functions will also basically have the limit, if we extend the limit to the numerator and the denominator, they will also be approaching L at some point. So that is why we have the L'Hopital rules valid with the derivative of the function. We have to be careful because we need to verify first that the limit of the derivative exists, then we can say that we can use the L'Hopital rules. This is an example of how we use it. Remember these limits that we have. If we evaluated x in 0, we will have 0 in the numerator, 0 in the denominator. So what we need to have is to evaluate the derivative of sin of x will be cosine of x, and g of x will be 1, right? We see that the limit exists for a number in the real line, then we can substitute and say that the limit of sine of x over x will be the same as the cosine of x over 1, which is 1, and if we do the evaluation, which is 1. Okay. Thank you.